Good morning. It seems like a long time since we've been together. I hope you had a good holiday. So make sure you have your calculator and a paper and something to write with handy today. We're going to be doing some practice problems. Today's lecture is actually very important. We're going to be looking at some really critical calculations. I also want to talk about the homework and the practice quiz. There are some things you need to pay attention to make sure that you're not going to miss points when we have a quiz or exam. So first, make sure that you check your quizzes, check your mistakes. A lot of times I write comments, so make sure you look at all the questions to see if I left you some comments. Some things to note for the short answer questions, you don't need to write those on a paper and take a picture. Just write them in a text box. It's faster, it's simpler. You know, unless you're writing a reaction or something complicated, if it's just simple words, then type it in the text box. It'll save you a lot of time, because when we take quizzes, you're not going to have a lot of time. So you don't want to mess with pictures and that kind of thing. For the calculations, okay, there are several things you need to pay attention to. This is true for quizzes. This is true for your homework. First, you have to always show me your work. Okay, that means your equations and the numbers you used. You have to show me both. You need to pay attention to significant figures. There were a lot of issues with significant figures, both in the practice quiz and in the homework. You need to pay attention to those. You need to pay attention to units. If a number needs units, you need to have them. You will lose points if you do not do these things. Also, you need to make sure you write your name and your student number on every picture. And if I'm not able to read it, it's wrong. So you have to make sure you write so I can read it. And then one note about the pictures. Some of you are filling up a whole page with information and then trying to take a picture. And those pictures are not clear when you put a lot of extra information in the picture, or if you try to do all the problems on one page and just take one picture that you send different times, then I cannot read it clearly. It's blurry. So you have to try to keep, your work. Normally you shouldn't need that much room. So one picture for each problem, and don't put several problems together in pictures. It makes it too hard to read. The resolution is not good. So you need to pay attention to that, both on your homework and then when we have quizzes as well. I do want to just talk about the matching question. So remember, the instructions were to give your answer as a number and a letter. I gave you this example in class. This was not the one on the practice quiz, but so for your answer, the biggest animal listed, well, that's of course the elephant. So you need to write 1C, and then smallest 2E, and then 3D. So your answers for the matching need to be in this form. I don't want you to write the words. Some of you decided to make up your own choices. If you make up your own choice, it's wrong, okay? Don't make up your own choices. And you shouldn't use choices more than one time unless I tell you you can. So make sure you follow the directions for these matching problems. Okay, so that was the practice quiz. There's still a few of you that need to take it. There were some of you that are confused about what time you'll be taking quizzes. And again, I will state, if you are in China, you will take the quiz at 8:30 in the morning. You don't have a choice. The choice is only for those that are outside of China. Okay, so for the homework, again, lots of mistakes, lots of comments. So again, make sure that you check the comments. If you turn your homework in early, then by the time class starts, I will have graded it. So you can already look at it and see what you did wrong. If you turn your homework in at the last minute, then I haven't looked at it yet. So just something to keep in mind. Okay, so on your paper, if I don't make any comments, if there's no marks on the paper, that means you did it correctly. So I only mark something if it's wrong. If I'm asking for work, that means either you didn't show me an equation or you didn't show me a number. If I write math, that means that it looks like your equation is correct, your numbers are correct, but your math is wrong. If I put question marks, that either means I have no idea what you did, which is never good, or it means I can't read it, and then it's wrong. Okay, units, significant figures, we already talked about. And again, your name and your student number have to be on each picture. And starting next week, if you do not put your name and student number on the picture, you will not get full credit. Okay? All right, so that's general about the homework. Now let's look at specific. So question 8 gave you a bunch of numbers, and then it asked what is the LOD at 99% confidence. So remember, the equation for LOD at 99 is the average of the blank plus 3 standard deviations. So that means you need an average and you need a standard deviation. So these are two things you should know how to calculate. You can use your calculator if you have a scientific calculator, which you should. Your calculator can do this for you, and you should learn how to use that. So if you put the numbers in correctly, this is the average for the blank, 0.17, and this is the standard deviation. And notice these have units. These are part per billion. Okay, then to calculate A, that's just 3 times the standard deviation plus the average, so you should have had 0.35 part per billion. Okay, B asked for the limit of quantitation. So remember, that's the average plus 10 standard deviations. So that's 0.76. And then C asked, okay, now I have a sample and the signal is 0.69. And it wants to know, can you measure that? So notice that that number is less than the limit of quantitation. So you cannot measure it. You can detect it, but you cannot measure it. So that should be your answer. Okay, and then just to review again these numbers, we take a blank, we measure it several times. Okay, I get an average. Here it was 0.17. And some are higher, some are lower. So 3 standard deviations. This is the point where you can begin to detect a signal. You can say the analyte is present. Okay, this limit of quantitation, this is the place where I can begin to measure the analyte. If the signal is between these two numbers, then we can detect it, but we can't measure it. Okay, so that was the question from chapter 1 on the quiz. Okay, let's go ahead now and turn to chapter 2. And before we do that, I'm actually going to go ahead and ask everyone that's here to go ahead and send me a message in the chat with your name and student number so that I know that you're here and you're here on time. So everyone that's here in the chat, send me your name and student number. And you need to do that right now so I know you're here and you're on time. Okay, for those of you that are watching on video, I will tell you later how to register your attendance. Okay. If you are here live and sending me your name and student number right now, you do not need to do anything else. You told me you're here. Okay, there's still 5 people that have not sent me their name and student number. So if you don't send that to me, then I think you're not here and you'll be absent. So name and student number. Okay, so last time we just started chapter 2, and remember chapter 2 is an introduction to spectroscopy. So we talked about what is the definition, what is spectroscopy? And we said it's the interaction of electromagnetic radiation and matter. So this is a definition that you should know. Okay, this interaction of electromagnetic radiation and matter. Then we said, well, what is electromagnetic radiation? And remember, that's a form of energy that has both wave and particle properties. And so we looked at the equations to describe that. And we said if you take all the kinds of electromagnetic radiation, you put them together, you get that thing called the electromagnetic spectrum. So your homework for last time asked you to deal with that information, to do a couple of simple calculations, calculating the frequency and the energy for an absorption band. Most of you did that correctly, except for significant figures. Okay, notice this number they give us has 4 significant figures. That means your answer should have 4. You know, the speed of light and h are constants. You can go get those numbers with as many significant figures as you need. So your answers should have had 4 significant figures. Then number 2 was about putting different regions of the electromagnetic spectrum in order of wavelength and of energy. And so here are the answers for those. Okay, so that was from last time. Last time we also talked about how does electromagnetic radiation interact with matter. And we said that we have these things called transitions. Transitions are interactions of light and matter. And for a molecule, there are 3 kinds of transitions. Okay, what are they? Do you remember? You need to know these 3 types of transitions. They are rotation, vibration, and electronic. Okay, so we looked at, okay, if we want to look at the energy change for a molecule, that's actually the sum of all of these. And we talked about if I have a molecule, I can show an energy diagram where my electronic transitions are from going from E0 up here to E1. Those are the biggest transitions. And then we said we can also look at vibrational, and we represent those by, like, this would be V0, this would be V1 and V2 and V3. Those are smaller energies. And then rotation, that's these lines here. So if we had a transition that just absorbed a little bit of energy, you know, from R0 up to R, looks like about 4, that's a rotation. So we use these diagrams to represent these to represent these transitions. Okay, that's for molecules. Now, for an atom, remember an atom only has 1 kind of transition. Which one? Okay, that's the electronic. So for an atom, it's much simpler. You just have the E0, E1, E2, E3. No vibrations, no rotations. And remember, that's because atoms don't have bonds. And to have a vibration or a rotation, you need bonds. Okay, then we also said, okay, spectroscopy is the interaction of electromagnetic radiation and matter. Sometimes another way to define spectroscopy is the study of spectra. So what's a spectra? Well, a spectra is a plot of intensity versus wavelength or frequency. We'll concentrate on wavelength for our class. So along comes some light, and if it has the right energy, we can measure this energy, which we measure as wavelength. Remember, energy and wavelength are related. And then we also measure how strongly that energy is absorbed. And that's the intensity. So we make these plots that are intensity versus wavelength. And these are called spectra. So in spectroscopy, we study these spectra. Okay, so all of that we talked about last time. So we're now ready to move on to some new material. So we want to look a little bit more about this idea of spectroscopy. So for atoms, we have an atom that is a nucleus surrounded by electrons. So it's actually those electrons that absorb the light energy. And the lowest energy for an atom is its ground state electron configuration. These should look familiar from your previous chemistry classes. So these are the ground state for, say, sodium atom or potassium or vanadium. So when we talk about an atom absorbing light energy, it's usually these outer electrons, what we call the valence electrons, that are absorbing that energy. So if they absorb light, they're going from the ground state. So from, say, for sodium, they're going from, say, a 3s, say, up to a 4s or a 5s to a higher energy orbital. Or if it's an emission, that electron is already in a higher energy and it's coming back down to the 3s and emitting light. So the experiment for absorption, we call it atomic absorption spectroscopy, and we abbreviate that AAS. Okay, and this will actually be chapter 5 in our book. So the experiment is to take your atom, okay, and we're going to take light and we shine it in, and then we measure the light that comes out to see how much was absorbed. And so the electrons are going from that ground state up to excited states. And then we get a spectrum that, again, is going to be here absorbance versus intensity. Okay, and that's what we're going to measure. We can do the same thing with emission, atomic emission spectroscopy. Now, you may think that this should be AES, but it used to be AES, but now it's called optical emission spectroscopy because AES is used for another method. So OES, optical emission spectroscopy, is what we use here. So here my sample has absorbed energy. The electrons have been excited, maybe by heat or by light or by chemical reaction. Doesn't matter how. And then they're going to come back to a lower energy and emit light. And we would get a spectrum that looks like this. And I'll just remind you, okay, so notice that this energy here is the smallest energy, but that is the longest wavelength. So remember, as energy increases, the wavelength decreases. So we always have to kind of flip those in our mind. So those are what atomic experiments look like. And this is an example of what some emission spectrum might look like. Notice that they're just very narrow bands and that each element has a different spectrum. We can actually use these spectrum to tell me what element is this, to identify the elements. Okay, so that's atomic spectroscopy. And we're going to learn a lot more about atomic absorption in chapter 5. All right. Oh, and by the way, each one of these lines can be assigned, you know, like the lines at 589 nanometers. We know that's a 3p electron going down to 3s. We won't worry about that. It's complicated, but they can actually determine what each one of those lines, what the transition is. Okay, now let's go back to molecular spectroscopy. So we said an atomic energy diagram looks like this, very simple. Molecular, much more complicated. We have the electronic levels, but then we have the vibrational levels. And then remember, on top of these vibrational levels, we also have rotational levels. Okay, so when we're doing an absorption experiment for molecular spectroscopy, absorption would look like the atom. We're going from the lowest energy up to a higher energy, but we don't just go to the E1, we also have vibrational levels. And then there's also rotational levels in here. So we get these bands that are very broad. Okay, for atoms, you get very narrow bands. You just get kind of these line spectrum. But for molecules, we get broad bands. So this is what an absorption light spectrum might look like. Here's an emission. Okay, same idea. We go from the excited state back down to the ground, but we can go to all of these vibrational levels and also all of the rotational levels. And so again, we get a broad band. And we will look at the absorption of molecules in detail in chapter 4. Here's actually a real life absorption spectra. So this is 2 of the pigments in a leaf, and you can see these broad absorption bands that we get. And here's an emission spectra. Okay, here's actually a picture of an absorption spectra. Now, do you think this is for a molecule or for an atom by how it looks? Okay, well, notice we said the atomic bands, they're very, very narrow. So we see all these narrow peaks, you know, here and here and here, and those look like atom peaks. But this one is broad. This one looks like a molecule. And in fact, this is a spectrum for something called brine. It's a very concentrated salt solution. And so it has both molecules and atoms. Okay, so this clearly shows you the difference between atom peaks and molecules. Atoms very narrow, molecules very big. Okay, so those are the absorption spectra. Now, what we're most interested in is, we said, okay, spectroscopy is the interaction of electromagnetic radiation and matter, and we study spectra. So what kind of information can the spectra give me? Well, the spectra gives me both qualitative and quantitative information. Now remember, qualitative analysis means what? Means what is it? So we can use spectra to answer that question, what is it? If we have an atom, then the wavelengths actually tell me what element it is. If you have a molecule, then the wavelengths actually tell you what kind of functional groups you have. So it can tell you, oh, you know, does the molecule have carbonyl, or does it contain benzene rings? Okay, so it can answer those kinds of questions. So the wavelengths give me qualitative information. What is it? Now, we can also use spectra to give me quantitative information. And remember, quantitative is how much is there. So the intensities tell me about how much. Okay, so remember, a spectrum is intensity versus wavelength. So the wavelengths tell me what is it? Qualitative. The intensity tells me how much, quantitative. All right, so let's look at how do we do quantitative analysis. And this is actually a very important method. We're going to spend a lot of time today looking at how we can do quantitative analysis. So to do this experiment, you start out with a light source and you measure its initial either intensity or power. And those two are related. The difference is the units. And both of these are related to the square of the amplitude. That's how big that wave bar is. Okay, so we measure the intensity or the power at the beginning of the experiment. And then we pass the light through my sample. And then some of the light is absorbed. And then we get a final intensity or power. Now, in order to do quantitative information, what you need is for your signal to be proportional to concentration. And it turns out the amount of light that is absorbed is related to concentration. And we're going to see exactly how it's related. But first we need to define some more terms. Okay, so here's my measurement. I have some light. I know its initial power or intensity, and I know its final power or intensity. So we can talk about something that's called transmittance. Okay, transmittance is how much light goes through a sample. Okay, how much goes through. So transmittance is defined by the ending power divided by the initial, or the ending intensity divided by the initial. Sometimes instead of talking about transmittance, T, we talk about percent T. Okay, and percent T is T times 100. Okay, so that's transmittance. How much light goes through my sample? That's one way to make the measurement. Another way to think about this is instead of how much light goes through, to think about how much light is absorbed, how much is taken in by the sample. So absorbance is related to transmittance. It's the log, so we have to do log base 10 of the initial intensity divided by final, which is, notice up here, that's the log of 1 over T. So absorbance is minus the log of T. Now, both of these numbers are unitless. That means they have no units because the unit of P and P0 are the same. So the units cancel. Or here, the unit of I0 and I are the same. So they cancel. So we can talk about transmittance or we can talk about absorbance. Okay, they're both related, and sometimes we do one, sometimes the other. So let's get a better feel for what kind of numbers are we talking about. So these are the equations that we can have for transmittance and absorbance. So let's take the case where no light goes through. Okay, you have your sample and the light's going through and nothing comes out over here, nothing. Okay, so this P or I, okay, is going to be 0 at the end. So the smallest that T can be is 0. Okay, that's the bottom end. No light goes through. Now, the other case is all of the light goes through. This is the case where P and P0 are the same, okay, which means your transmittance is 1. Okay, so T can be between 0 and 1. Now, I told you often instead of T, we use percent T. Okay, so percent T here would be 100. Okay, it's 1 times 100. So transmittance can be between 0 and 1. Percent T goes between 0 and 100. All right, now what about absorbance? So if no light goes through, that means all the light has been absorbed. Okay, and so now we have minus the log of 0. Well, that's actually infinity. It's a huge number that we can't even measure. Now, what if all of the light goes through? That means no light's absorbed. None is taken in, so the absorbance is then 0. Okay, so notice absorbance can go from a very big number to 0. So here's this kind of figure that shows the two numbers together. This shows you percent T and absorbance. So notice, just like we said with energy and wavelength, we said when energy goes up, wavelength goes down. When wavelength goes up, energy goes down. Notice A and T are the same. When the absorbance gets very big, transmittance is very small. And when transmittance is very small, absorbance is very big. So you can see how the two are related here. Okay, now we have to be comfortable, you have to be comfortable changing back and forth between A and T. Okay, so we're going to practice some now. So remember the formula that relates them. Absorbance is equal to minus log T. So go ahead and pull out your calculator now. Okay, pull out your calculator. And let's say I have a percent T that's 50. Okay, if percent T is 50, then what is T? Remember, T is percent T divided by 100. So T is 0.5. All right, now what would the absorbance of this number be? Okay, so to take absorbance, you need to take the log of 0.5 and then minus that number. So your answer should be 0.30. So take just a minute with your calculator and go ahead and make sure you can do this math on your calculator. You have to be able to do this. Okay, so you just take 0.5, take the log, and then minus that. You should get minus 0.3, and then minus that number is 0.3. Okay, now notice, again, I already talked about as T gets smaller, absorbance gets bigger. And this table shows you some of these numbers. So notice when 100% T, absorbance is 0. If I have a T of 10%, the absorbance is 1. If I have a percent T of 1, absorbance is 2. Okay? Percent T of 0.1, absorbance is 3. Now, what you should realize is that when we start talking about these numbers here, okay, 1% of the light goes through. That means your signal is now very small. Most of the light is being absorbed. And what that means is those numbers are very difficult to measure. So normally when you're looking at absorbance, we always want to keep the absorbance less than 1. That's to make sure that we have enough light we can measure. Okay, when the absorbance gets up here at these really big numbers, the amount of light we're talking about is very, very small, and we cannot measure that. If you have a really good quality instrument, then you might be able to go up to 2. Okay, but often we kind of try to keep all absorbances under 1. Okay, so that's a little bit about absorbance and transmittance. Now what we want to do is just practice more. So keep your calculators. We're going to do a lot more practice converting between transmittance and absorbance, and then between absorbance and transmittance. Okay, so I have these two numbers, transmittance 37.2 and 3.2. So the first question is, are these T or percent T? Okay, remember I said T is between 0 and 1. Okay, these are bigger than 1, so they are percent T. Now, why don't I say percent T? Because it's practice to just say T is 37.2. And you are supposed to be educated and know, oh, that is percent T. So they don't always tell you it's percent T. You have to know if it's bigger than 1, it's percent T. All right, so to change these to absorbance, I need to divide by 100. So T is going to be 0.372. Okay, how about for this one? What would T be? This, remember, is percent T. So what's T? Okay, well, it's 3.2 divided by 100, or 0.032. All right, now calculate the absorbance. Okay, so we're going to just use this formula down here. We're going to put these numbers in my calculator. Take minus the log. Okay, so that first one, you should have, get my picture out of the way, 0.429. And the second one, you should have 1.50. Let me talk just a minute about significant figures. Okay, remember the rule for logs. We look at how many significant figures here, and we see there's 3. So this answer should have 3 after the decimal. That's the log rule. Okay, this one has 2. So this one should have 2 after the decimal. Okay, so that's converting T to A. Now, we need to also go the other way. What if I give you absorbance and I want transmittance? Okay, how would we do that? Okay, well, now we have to take an inverse log. And that equation is actually written down here. So T is 10 to the minus A. Okay, so for this one, you're going to have to take 10 to the minus 0.72. Okay, and if you put that in your calculator, you should get 0.19. Okay, now this is T. Now, what if I want percent T? Then I have to multiply by 100. So this should be 19%. So go ahead and try that in your calculator, and also try to do this one in your calculator. Okay, so you should have 10 to the minus 2.7 times 100. Okay, and then that's 0.2%. Okay, now let's talk about significant figures here. Okay, so here, this is an absorbance. Now remember, an absorbance is a log number. So the significant figures are here behind the decimal. This original number had 2 significant figures. So my answer should have 2. Okay, this one, again, absorbance is a log number. So significant figures are here. So the original number had 1 significant figures. So this is what you should have for the answer here, 0.2. Okay, so back and forth, you need to be able to do both ways. There is actually a problem in your homework, both problem 7 and problem 8. Okay, so we're actually I'm gonna give you time to try to do these right now. So 7 is to convert the absorbance data into percent transmittance. Okay, so go ahead and see if you can do that. I'll give you time right now to do that. There are still several of you or some of you that came late. You need to register your attendance. You need to send me your name and student number in the chat group. So go ahead and work on this problem. I'll give you a few minutes to do that.
Teacher, sorry. Teacher,
Yes.
I have a question.
Mm-hmm.
What's the difference between the absorbance and the absorptivity?
The absorbance and what?
Absorptivity.
Ask me that later at the end of class if you still don't know.
Okay.
Because I'm going to talk about absorptivity in a little bit.
Okay.
Okay, but they're not the same. But so if you're still not sure at the end of class, you can ask me again.
Sure.
Okay, so we have absorbance data that you need to get into percent T. So again, the equation you need is this. Okay, so 10 to the minus A. So the first one, you should have 0.527. Okay, B. Oh, and then it asks for percent T, so we have to multiply by 100, so you should have 52.7 for your answer. For B and C, same procedure, 10 to the minus A, and then times 100, so you should have 3.17% and 91%. Okay, that's from absorbance to transmittance. You also have to be able to go from transmittance to absorbance. So go ahead and take just a couple minutes and do these conversions. Okay, so transmittance. So again, these are bigger than 1, so these are percent %T. So you have to divide by 100 and then take minus the log. So the first one, you should have 0.524, and then you should have 0.0650, and then you should have 1.527. Someone asked about the significant figures on this one. So notice this number only has 2 significant figures. That means your answer can only have 2. Remember, that 0 is not significant there. That's a placeholder. Okay, so it is very important that you know how to go back and forth between absorbance and transmittance. So if we went too quickly and you weren't able to do all these calculations, you need to go back after class with your calculator and make sure that you can do this math. Okay, we will go ahead and take a break here. I will say one last time, if you are watching live, you need to send me your name and student number in the chat so I know that you are here. If you are watching this recorded, then you need to send me an email, or you need to send me a message in RAIN. You can do, if you can figure out how to do that, you can send messages to people in RAIN, and you need to tell me the number 37, 37, and then I will know that you watched this video. Okay, so we will go ahead and take a break there. Oh, by the way, I will mention many of you have sent me WeChat friend requests, and I have not accepted them. In general, I do not want to have all 150 of my students become my friends. So you have to, I'm sorry, you're going to have to use the group or email, or you can use RAIN to communicate with me, but I'm not going to do individual friend requests for everyone. Okay, we will take a break here, 5 minutes, and then we'll come back. Okay, so now we're actually going to look at how do I use this transmittance and absorbance for quantitative analysis. So remember the experiment. We have my sample. I shine some light through. I measure the power in the beginning and some power in the end. Now, a couple of terms we use. This thing that holds your sample, that's called the sample cell. It's also called a cuvette. Often this is a piece of quartz or glass. It's called a cuvette. And then this distance, the size of the cuvette, is called the path length. The path length. And we use the symbol B to indicate path length. Okay, so how does that help me with quantitative analysis? Well, there is something called Beer's law, and Beer's law is the most important equation in spectroscopy. It's also sometimes called the Beer-Lambert-Boger law. It's named after 3 scientists, but the one who did the most important work was Beer, so we will just shorten it to Beer and call it Beer's law. So Beer's law is very difficult to remember. It looks like this. It is A equals A, B, Z. Okay. Pretty difficult, huh? All right, so what Beer's law said, it says for monochromatic radiation, that means one wavelength, the absorbance is equal to this thing called A. So A is absorptivity. This is the term that one of your classmates asked me about earlier. So absorptivity is a measure of how strongly something absorbs. It's a constant, and for a given compound at a given wavelength, it's always the same number. Okay, if you change wavelengths or you change compounds, the number changes. Okay, so that's called absorptivity. It's a measure of the ability of something to absorb. Okay, B, we just saw, that's the path length. And path length, the unit is almost always centimeters. Some of you in your homework thought, oh, I need to change units to meters. Do not do that for path length. The unit is centimeters. And then C is our friend concentration. And concentration can be in any unit, part per million, milligram per 100 milliliters. But notice what this tells me. It tells me my signal absorbance is proportional to concentration. Quantitative analysis. Now, there is a special form of Beer's law that is if C is in moles per liter, then we write Beer's law like this. It's the same A, but now we use this symbol, and that's called the molar absorptivity, where the units are molar to the -1, centimeters to the -1. So these two equations are the same. The only difference is the concentration for C. If the concentration of C is molar, you use this equation. If the concentration of C is anything else, you use this equation. Okay, so Beer's law, one of these two forms, and notice there's a linear relationship between absorbance and concentration. So that means I can do quantitative analysis. So these measurements where we do quantitative analysis is called spectrometry. Okay, we looked at spectroscopy. So spectrometry, that's using spectra to measure how much is there. Okay, spectrometry. So let's look at a couple of calculations now with Beer's law. So here's a very simple one. You will never see one that is this simple in the homework or on the quiz, but we'll start here. So the molar absorptivity of a compound is 1.5 molar to the -1 centimeters to the -1. And they want to know what's the concentration of a solution that's made from this chemical. It has an absorbance of 0.72 and a path length of 1.1 centimeters. Okay, so notice the absorptivity is molar, so we're going to be using this form of the equation. And notice they have given me the absorbance, they have given me the absorptivity, they have given me the path length. So I just need to put all the numbers in and solve it, and I get 0.44 molar. Okay, so this is a very simple, straightforward calculation. Now, in real life, you will never do a calculation like this. Here they have given you the value for absorptivity, probably from the literature, and you can never use this number from the literature because sometimes you'll be doing your measurement under a little bit different conditions, and so the number that you would get in the lab would be a little bit different than this. So you never use a number from the literature. In fact, the most common way to use Beer's law is to use a calibration curve. And we'll look at how you do that. But first, let's look at another example of a calculation. This one is the kind that you will see in your homework and maybe on a quiz or on an exam. So here you have a solution of compound X, and they tell you the concentration, and they tell you the transmittance, and a 1 centimeter cell. Okay, and we're measuring at 500 nanometers. Okay, now we have an unknown, and they tell you its absorbance. They tell you it's in a 5 centimeter cell, and they want to know what is the concentration of the unknown. Okay, so let's think about what do we have here. We have two different solutions. Okay, and so the first one, and these are the different things we can know from Beer's law. So notice that for this first solution, they tell us the transmittance, they tell us the concentration, and they tell us the path length. Okay, so we know all of this about this solution over here. Now, this solution over here, they tell us the absorbance, they tell us the path length, and they want to know what is the concentration. Now, how can we do this? Well, both of these are the same compound. So remember this guy, the molar absorptivity. I said it's a constant for a given compound at a given wavelength. So here we have compound X at 500 nanometers. So that molar absorptivity is the same for these two solutions. That is what links these two things together. So by rearranging Beer's law, we can use the first set of data, the data that we have for this, and we can calculate this molar absorptivity. And then once we know the molar absorptivity, now I can calculate the concentration for this solution. Okay, so let's go ahead and do that. So the first thing we need is the molar absorptivity, because that doesn't change. But notice the transmittance, they've given us transmittance. I need absorbance. So that first thing, change transmittance to absorbance. Then calculate molar absorptivity for that first solution. And so I get this number, 8.09 times 10 squared. And notice the units, molar to the -1, centimeters to the -1. All right, now I'm ready to look at the unknown. Okay, so now I know the absorbance. I know this number. I just calculated it. I know the path length. And notice the path length's different for this one. It's 5. So I put those numbers in, and I get my answer, 1.7 times 10 to the -4 molar. Okay, so you will see that kind of calculation. And it's just practicing using Beer's law and rearranging the equation. You know, sometimes you're looking for molar absorptivity, sometimes C. Okay, so you'll get to practice that. Okay, but as I said, even this way would not be a common way. You would not do this in the lab either. The way we actually use Beer's law is to make a calibration curve. So let's see how that works. So first thing I'm going to do, I take my sample and I measure a spectrum. Remember, the spectrum is the absorbance versus wavelength. And then I'm going to take the maximum wavelength, and we'll talk about that in future chapters. And this is where I'm going to measure my absorbance. So I'm going to make some standards. I'm going to make a blank. I'm going to measure the absorbance, and I'm going to get the equation of a line. All right, now, how does this help me with Beer's law? Well, remember, this line follows Beer's law. The equation of this line, notice that the y is the absorbance, and x is C. Now, notice this C is milligrams, so we're using the A, not the molar absorptivity. Okay, now I know the slope of this line that I would get, from plotting the line. And what do we know that slope is equal to? Okay, well, notice the slope is going to be equal to this right here. The slope is equal to the absorptivity times path length. Or if we were doing molar absorptivity, it would be molar absorptivity times path length. So if I want to know what is the absorptivity for this, how would I get that? Well, notice that absorptivity is simply the slope divided by the path length. And you will see a problem like this in your homework today as well. So two different ways we do calculations with Beer's law. Sometimes we have two different solutions like the previous. More commonly, you would have an equation of a line, and you have to do a calculation that way. Okay, so that's Beer's law. Now, Beer's law is quite reliable. Most of the time you're going to get this nice straight line, but sometimes the line will not be linear. And so we want to talk about a couple of reasons it's not always linear. If you remember in chapter 1, I talked about the calibration curve. And we talked about this upper limit, the limit of linearity. We said we get to high concentration and that line starts to curve. It's no longer linear. So if you're working at high concentrations, Beer's law will not be linear. And there's two reasons for this. The first is at high concentration, your molecules start interacting with each other, and that changes how they absorb. The other reason is at high concentration, the molecules are absorbing most of the light, and then there's very little light left. Remember, we looked at these values. We said, when the absorbance is 1, only 10% of my light is left. And an absorbance of 2, only 1%. An absorbance of 3, only 0.1%. We said, when you get out to these low levels of light, out here, you can't make good measurements. So we have problems with Beer's law. Another reason we sometimes have problems with Beer's law is sometimes there's other species. So remember my experiment. I have my beginning light that I measure its intensity or its power, and then I'm measuring here. And when I do this, and I calculate transmittance or absorbance, I'm assuming all the light that was absorbed was from my analyte. But sometimes there are other processes. Some of the light may hit that cuvette and bounce off. Some of it may hit some particles in here and scatter. Okay, so these then will make my absorbance or transmittance wrong, okay, because I have other processes. So that's So that's another reason that Beer's law will sometimes not follow the rules. Okay, and we will look more at these deviations when we get into chapter 4 for that. Okay, now we want to go back and talk a little bit more about calibration curves. Okay, so we talked about how we make these. We said that the reason we have to do a calibration curve is it will determine the relationship between my instrument response and my concentration. Okay, for Beer's law, the instrument response is absorption. So the curve is what determines that relationship. And in chapter 1, we said, okay, the first thing I have to do is make a blank, and then I make several standards. Okay, now remember, what's a blank? The blank is the thing that contains all the same things as your standards, but no analyte. Remember, the concentration of the analyte in the blank is 0. And the job of the blank is to set that baseline, to set the 0 point. As we look in later chapters, we'll see the blank actually helps correct for different interferences. It's a very important thing to have. But for an absorbance measurement, we use it to set 0 because we know the absorbance of the blank should be 0. Okay, and then we also make standards. Remember, what's a standard? The standards are solutions that I know the concentration of the analyte. So we make the blank, we make the standards, we measure the signal for each of them, and then we get my line. Okay, now, it's best if that line is linear over the whole range. But what if it's not linear? What if we actually get a line that's at higher concentrations is no longer linear? Well, sometimes that's okay, but usually it's better to just dilute. So let me show you an example. So here is a calibration curve. And so we've got my blank and several standards. And notice that it's a nice linear curve down here at low concentrations. But as we get to higher absorbance, we're getting away from the linear line. Now, you have two choices to deal with this. What if your sample has an absorbance out here? You can see there's a very big error between the curve and the line. Well, you can try to get more samples in this area and try to get a line just for the high region, but it's actually better to actually dilute, okay, so add some more solvent and bring that concentration back down in this area where the absorbance is less than 1. So that's what it's talking about here. Sometimes it's okay to, if you can get more standards at that high concentration, but the best solution is to dilute it to get the absorbance back down to a lower concentration. Okay. All right, so next we want to talk about that one thing that's important for your curve is that the sample and the standards, they need to respond the same way. And sometimes they don't. Sometimes your sample has things that your standard doesn't. This is called the matrix effect. So for example, let's say I'm trying to measure sodium in wastewater. So wastewater is very dirty water. It contains lots of stuff that will probably also absorb along with the sodium. So if you make your standards, usually your standards are very clean solutions. So now your standards in your sample, they behave differently. And that's going to cause a big problem in your calibration. Another example, if you're trying to measure calcium in the presence of phosphate, phosphate will lower your calcium signal. Okay, so this is called the matrix effect. Something in your sample is interfering with your measurement. So we have a way to deal with this, and that's to use something called a standard addition calibration. So this is going to sound kind of strange, but what you're going to do is you're going to take your sample, say that wastewater sample, and you're going to add it to all of your standards and all of your blanks. Okay, so here is my blank, and then these are my standards. So notice this standard had 5, and this had 10, this has 15, this has 20 milliliters of standard. Okay, but first what I'm going to do is take my sample that I'm trying to measure, and I'm going to put it in my blank, and I'm going to put it in every standard. And we're going to add the standard, and then we dilute. Now, why would we do this? Well, remember, your sample has this matrix that's causing problems. So what I'm going to do is I'm going to add that matrix to every standard to the blank. So now these will all behave the same way. Okay, now everything behaves the same way. The matrix now affects the blank, and it affects my standards in the same way that it affects my sample. So this is just the procedure. We spike the unknown into all of the standards and the blank. And by doing that, we compensate for the interferences. And so we can compensate for this matrix effect. Now, notice we have put my unknown in the blank. So when you make your calibration curve, notice the blank actually has a signal because I put my unknown in there. So you can actually trace this line back. It's called extrapolate here, and this is the amount. This will tell you how much of your analyte is in your unknown. Okay, and that's what this statement right here is talking about. Okay, so for the main thing that you should know about this kind of calibration, standard addition, right here is what you need to know. It compensates for the matrix effect. There is another kind, the one kind of matrix effect that it doesn't compensate for is spectral interference. If you remember in chapter 1, there was that plot where we had the MNX and the iron X. We said, this iron is interfering with the magnesium, not magnesium, manganese, and that's called a spectral interference. This method will not work for this kind of interference, but it will work for something like the sodium in wastewater. All right, one other special kind of calibration method we have to look at, and that's called the internal standard. So this one's a little bit different. This one you're going to find some other standard, an outside standard that you're going to add to your sample, to your blanks, and to your standard. And then what you're going to do is compare a ratio of your analyte standard to the internal standard. And we'll come back and talk about why, but let me show you the problem, and then it'll be a little bit clearer. So let's say I'm trying to measure lead in my sample. And so I'm measuring the same sample. And notice at 8 a.m. I get this number, at 10 a.m. I get this number, at 1 p.m. this number, 3 p.m. So you can see the numbers are jumping everywhere. There's something changing in the instrument that's causing very bad measurements. This is the same sample. You should always get the same number. Okay, so this kind of problem is called instrumental drift. There's something in the instrument that's changing with time. So how can we fix this? Well, we find something else that I'm going to put in. And the idea is that as the instrument's changing with time, both my sample and the internal standard, they will both change together in the same direction, so that the ratio of these two should always be the same. And now it can be hard to find an internal standard because it has to have a different response than your sample, but you want it to be similar, but also that you can tell it apart. Okay, so in this example I gave you, the lead jumping all around. So then the internal standard here is the bismuth. Now, notice the numbers for bismuth. They're jumping everywhere too, up and down. But notice the ratio between the two. The ratio is very consistent. So when one goes up, the other goes up. They're always going together. And so the ratio gives you a very nice measurement. Another example of the same thing. Here we're determining sodium. And so here they've actually got different concentrations. And so we've got the measurements for sodium and for lithium. Now, if we just look at these numbers, we don't really see that there's a problem. But notice the calibration curve for just the sodium. Again, this is not a good curve. The points are, some are high, some are low, they're all over the line. So this again is that problem of instrumental drift. But when I compare it to the lithium, now I look at the ratio, which is the lithium's the internal standard. Now notice this line, very nice calibration curve. Okay, so internal standard method corrects for instrumental drift. So you should be aware of these two special kinds of calibration. The standard addition for the matrix effect and the internal standard for instrumental drift. Okay, that actually finishes chapter 2. So for your homework, you're going to be doing 3 problems, so 9, 10, and 11. These are all Beer's Law questions. And you're going to submit these on RAIN, as always. So remember, 1 picture for 1 problem. Don't put them all on 1 paper and take the same picture over and over. Then I can't see the details. And again, okay, this is probably the last time I'm going to say this, but make sure you show me your work, you watch your significant figures, you include units if you need them. You should always circle your final answer so that I clearly know this is your final answer. Make sure your name and student number is on every picture. And then you need to make sure that you know how to answer all the questions in the book. Okay, we've now finished chapter 2. And a few of them I've said turn in, but there are many other questions that are important that you need to make sure you know how to answer. And I have actually given you the answers to those already, but make sure you're looking at all of those questions in the book. Okay, so at this point, you should have given me the following information. I should have your student information form. You should have sent me some verification that you attended the first lecture, the first week. Should have given me 2 different homework assignments, one for chapter 1 and one for chapter 1 and 2. You should have done the practice quiz. You should have given me your attendance for today if you're listening live. If you're watching this on video, I told you how to do that. And then there will be another homework that's due next week. So you need to make sure that I have all of these things from you. There are still several students that are missing things. So please make sure that I have all of this, because if you're missing things in the end, it will affect your final grade. Okay? All right, we still have some time left. So we are going to go ahead and look at chapter 3. We won't get all the way through it, but we'll get a little bit into it. It's kind of an introduction. Chapter 3 is actually a very short chapter. So let me get this going. Okay, so chapter 3 is called Optical Components. The optical part means that this is spectroscopy instruments, and the word component means parts. So we're going to be looking at the parts of an instrument that measures the spectrum. So there's lots of different kinds of instruments. There's some that measure absorption and some that measure scattering, and there's others, but these 3 types are the most common, and all of these instruments actually have the same components. The inside, the basic parts are the same. So remember, in these instruments, we're measuring wavelengths that are absorbed or emitted or scattering, and we're measuring the intensity. So we're getting these spectra. Okay? So the instruments that measure these spectrum are called spectrometers. Okay? That's the name of these instruments. And as I said, the components, the parts for these are all similar. So there are 5 basic parts for optical instruments. The first one is the radiation source, the light source. Okay, we're doing spectroscopy, interaction of electromagnetic radiation and matter. So we need a radiation source. Then you need something to hold your sample. You need something to select the wavelength. You know, if I'm measuring the spectrum, I want to measure absorbance at 500 nanometers. So I have to have a way to select 500 nanometers. You need a detector. You need something that's going to measure that absorbance, you know, the P0 and the P. And then you need a signal processor. In all modern instruments, the signal processor is the computer. So we won't talk more about that. Okay, so, oh, what did I just hit? That was very wrong. Sorry about that. Let me get that fixed. Okay, sorry about that. Okay, so here's a figure that just shows you kind of these 5 different parts in different kinds of instruments. So notice absorbance, there's a source, the wavelength selector, the sample holder, the detector. In emission, we have those same things. Sometimes the order is different, but all of these instruments have the same 5 parts. And for our class, we're only going to be looking at absorbance. So we don't really have to worry about these other 2, but I just show them so that you see all of these have those same parts. Your book actually has some tables that show you the different kinds of sample holders, the different kinds of wavelength selectors, the different kinds of sources. These are the radiation sources and the different detectors. And as we go through different parts, some of these names you will need to learn. Some of them you will never need to learn. So I will just tell you what you need to know. But just good to know these figures that kind of show us everything together are in your book. Okay, so let's actually look now at the radiation sources. So what do I want for a radiation source? What will be important? Well, these are kind of obvious if you think about it, but the first thing is you want your radiation source to emit the wavelengths you want to study. So if I want to study 500 nanometers, my source needs to give me 500 nanometers. I want my source to give me enough light that I can easily detect it. You know, if the power is very, very small, that's not a good source. If I'm doing molecular spectroscopy, I want the intensity to always be the same for every wavelength. Now, we'll see we're not going to get that, but that's what I'd like to have. Also, it's important that the intensity doesn't change, okay, fluctuate, that means change with time. And there's two ways that it can change. One is over a long time, the intensity can slowly get higher or slowly get lower. That's called drift, and I don't want that. I also don't want short term, and that's flicker. That's if the intensity is doing this kind of thing, and I don't want that either. Okay, so looking at that table in the book now, what's important is to notice that the types of radiation sources can be divided into two types. We have what are called continuum sources and line sources. Okay, so these continuum sources, these are the ones that give me radiation over a wide range of wavelengths. Okay, so notice the intensity is changing very slowly. Okay, so the intensity difference between here and here is small. There's not a big change. Now it is changing with wavelength. Okay, remember what I said, what I'd really like is to have a very high intensity that was the same at every wavelength, but that's not actually possible. So this is typically what they look like, and notice they change slowly with wavelength. One note about the English, notice that this word is continuum. That's different than the word continuous. Okay, the word continuous means constant with time. Okay, this kind of source is called continuum, so a little bit different words. All right, so there are different sources for different regions, and right now you don't need to know the names of these sources. When we get into chapter 4, we'll actually look at this deuterium, and we'll look at the high pressure xenon, and we'll look at tungsten. But for right now, you don't need to know the names. What you should know is that continuum sources are used for molecules and for a kind of emission. Okay, but again, what we will be focusing on is molecular absorption. Okay, so we said there's two kinds of radiation sources, continuum and line. Now, the lines are different. They only emit a few wavelengths. And notice the intensity is a strong function. So right here, at this exact wavelength, the intensity is very strong, okay, at 285. But if I move even a little bit, the intensity goes to 0. So I get very sharp lines and only a few lines. Those are the line sources. And again, we'll be looking at these in more detail in chapter 5, but these are the names of some line sources. Right now, you don't need to know them, the names, but what you should know is that this is what we use for atoms. Okay. There is one other important line source, and that's something called a laser. And these can also be used for Raman and fluorescence. Okay, so those are the sources. Two kinds, continuum and line. Continuum is used for molecules. Line is used for atoms, mostly. That's what you need to know about the sources. The sample holder is also pretty quick and easy. So we need something to hold my sample. It has to be transparent to the light. You know, if I want to put my sample in this would be a bad sample holder. The light can't go through that. Also, this is way too big. So your sample holder has to be the right size and the right volume. It has to have a good pack length. So there are 3 kinds of sample holder materials that you should know. So if you're going to work in the UV, the sample material we normally use is quartz, okay, quartz, or sometimes it's called fused silica. If I want to work in the visible region, then I'm going to use glass. And if I want to use in the IR, we would normally use sodium chloride or potassium bromide. Okay, now these, you think, oh, that's a salt, that's not clear, but you put them under pressure and they will actually turn transparent so the light can go through. So this shows you some of the different kinds of sample holders we have. So notice we said that quartz, notice it works down here from the UV all the way up. And then we said in the glass, notice glass starts here in the visible. It's not good down here in the UV, and then works up. And then here's the sodium chloride in KBr. Now, question, can you use quartz in the visible? Well, notice, yeah, you can. Okay, but if you're only going to work in the visible, glass is better. Why? Well, glass is much cheaper than quartz. Okay, so if you break a glass cuvette, it's much cheaper to replace than quartz. So usually if you're in the UV or UV vis, we use quartz. But if you're only in the visible, we use glass. Okay, so we said the instruments have these 5 parts. The first one was the radiation source. I said there are 2 kinds. They are continuum and line. Continuum I use for molecules. Line you use for atoms. Then we said we need a sample holder. So we said if I'm in the IR, I can use NaCl or KBr. If I'm in the UV, quartz. If I'm in the visible only, glass. If I'm in the UV vis, quartz. All right, that's what you need to know about these 2 things. So pretty straightforward. All right. Next time we will look at the wavelength selector and the detector. And so next time we will finish chapter 3 and we will actually go ahead and start chapter 4 as well. Okay. And just to kind of give you a heads up, in 2 weeks, we will have our first quiz. That will be on chapters 1, 2, and 3. So I recommend as you have time now, you should be starting to study that material so that you're not surprised when the quiz comes. Okay, that's it for today. And I will see you next week.